First of all, we can talk about the lithium ion cell manufacturing. So the conventional cell manufacturing process include the mixing process and the coating, then pressing or calendering we can say, then slitting, sometimes notching, then cathode anode winding itself. They are collaboratively go to the lamination process or the winding process. After winding, we have a folding process, then a welding or maybe insertion of jelly roll inside the case, then sealing, electrolyte filling, then formation or aging, then sorting. Sorting is a kind of grading, like the capacity wise we grade the cell, then recharging of the cell, and final packaging. So this is a kind of a very conventional process including in all kinds of formats, but we will start with each of the process one by one, and I will tell you like what are the formats and what are the processes involved in each formats, for example cylindrical, prismatic, or pouch cell. So let's start with the mixing process itself. So mixing process start with the materials, the making of slurry. So during this, what are the material I wanted to tell you here. So materials are like the cathode material and anode material. So in cathode, what materials we have is the lithium cobalt oxide. This is generally used in the phone batteries, which has a capacity of 140 mAh per gram. It is somewhat similar to LFP batteries as well. Then lithium manganese oxide, LMO battery. So its specific capacity is 100 to 120 mAh per gram. So this mAh per gram is tell you a very important thing, like you wanted to made, for example, a 5000 mAh battery. So for 5000 mAh battery, how much gram of active material you wanted to use? This MAS signifies you that based on that you add the material inside your slurry with the certain composition so that you will achieve this, and accordingly the thickness and weight also will come into picture, that I will tell you once we go to that process as well. So another one is the lithium iron phosphate. This is LFP batteries we can say, LiFePO4. So its specific capacity is nearly around 160 mAh per gram. And the NMC batteries, these batteries and LFP batteries are more overused in the electric vehicle nowadays. And NCA battery or lithium nickel cobalt aluminum oxide. So these batteries are used by Tesla in their electric vehicles. Apart from that, LFP batteries and NMC batteries are currently used in our electric vehicle nowadays. And in India, LFP is more suitable one as compared to NMC. And another one is lithium titanate. So it's another battery. It has a very huge or we can say a large cycle life, but because of the titanate it's costly, so this battery is very costly, but the lifespan is very good for this battery. So it also has a capacity of 160 mAh per gram. So against these cathode material, we have another anode material as well. So this is a more commonly used anode material, which is graphite, so which has a specific capacity or generally a theoretical capacity of 372 mAh per gram, but the practical capacity is somewhere around 350 to 355 or 360 when we are using as a material. And the lithium titanate again, so it has a specific capacity when we use as an anode, so it has a specific capacity of 175 mAh per gram. This is a very important material where the scientists are doing a lot of research on this to use silicon as a anode material. But a part of or let's say a percentage of silicon we can blend with the graphite to use as an anode, but we can't use pure silicon because it has a expansion issue during the process or during the life cycle. That's why we are not using. So some companies are using 2%, 3%, 5%, or maximum 9 to 10%, not more than that. 9 to 10% is also very severe because it has a huge expansion. As compared to graphite, it has 400% expansion. So we can understand over the period of time the battery will swell or maybe a kind of blast situation will happen with the silicon. So it's under research right now itself. Another one is graphene. So graphene is a single layer structure we can say. When the graphene layer are structured together or clubbed together, it makes a graphite. So graphene is kind of 1D or 2D structure which has a high amount of specific capacity we can say because of this structure, and it is unorganized structure, so we can store enormous amount of lithium ions in it. Then another is tin and tin alloys, which has a specific capacity of 300 to 400 mAh. And another one is lithium metal, 3860 mAh per gram, which is a theoretical capacity. And this is what, so these are the materials that we are using as an anode and cathode material. Now we jump next. So during mixing process, we have certain kinds of mixture that we have to use. So mixers are like the planetary mixture. This mixture is used for the lithium ion cell manufacturing or the slurry making. High speed mixer is kind of this mixer, but we are not using any high speed mixture in this. And the universal type mixture is like we have this agitator inside the vessel and we directly mix it. So this is a kind of universal type vessel. A static mixer we are not using here. Extruder is like this, where we have this spring kind of system and there is a vessel where this mixture is rotating and everything is mixing. So here we can see the spring kind of system, and this is a kind of vessel, complete vessel. It's a cross-sectional view. So extruder also we are not using. Extruder generally used for the dry coating or dry mixing, not for the slurry mixing. So when we use extruder in a dry coating process or dry mixing process, not in wet mixing. So in wet mixing we use planetary mixer as an industrial production or pilot production. For the lab scale we generally use ball mill, or let's say uh, a thinky mixture. There is another term, a thinky mixture is also coming, where we use I'll show. So a thinky mixture is a kind of rotational mixture which has vessels in it, a space where we keep our boxes of slurry, and it is rotating. So through this rotation this mixing is happening. A ball mill is a conventional thing, like we have a system where we are putting our material and there is a balls that is dropping inside or dropping over the material to make the material uniform. So it's a kind of making the material uniform as well as mixing the material uniformly or creating the homogeneity inside the system. So these are the kind of slurry making mixers that we have right now. And again I'm telling you to understand the planetary mixers we are using for lithium ion cell manufacturing or the slurry mixing. Next is the slurry making process. So how we can make the slurry, and what are the materials we have in the slurry, and what are the importance, that I'm going to tell you one by one. So basically this is a real kind of stuff when we are talking about the battery. So slurry is one of the very important part including other manufacturing process. So slurry making is like we have to decide which material we are going to use, and we have the material that I showed you like NMC, LFP, graphite, LTO, LCO, etc. Which material we are going to use and what kind of slurry we are making, and whether it's anode material or cathode material. So again the binder also is the important thing. So active materials are the materials which are active inside the system or in the battery. Binders are the material that help us to connect the active material with my current collector or my substrate. For example, in anode, so copper is my current collector. For example, in cathode, aluminum is my conventional current collector nowadays. And to bind this black portion with this copper foil, I need certain binders. So there are some common binders, for example PVDF, PTFE, SBR, CMC. So these are some common binders used with certain solvents. So for example PVDF used with NMP but not with water. So that's why cathode slurry is made in NMP. And NMC material or the LFP material we can use the PVDF. So cathode generally mixed with PVDF or made with PVDF, whereas SBR and CMC used for the anode slurry more frequently. And these are both water-based binders. So we can mix with water, and the graphite also we can mix with water. So anode slurry we can made with water, so it's aqueous slurry, whereas the cathode slurry is a non-aqueous slurry. So this is also a very important point. Another terms we use is the additives. So additives are like the component which help us to increase the strength of the material as well as the flexibility. So for example, once the material is dried, it will not behave like a rigid or like a stone thing, so that if we fold our electrode it will crack. So to avoid these kind of issues, we add certain additives which create the flexibility inside the material. So some of the material or some of the additives are like C65. These are the conductive additives which will create the conductivity. Another one is the carbon black or pulverized carbon. These additives help us to create the conductivity inside the system. So slurry making requires some important properties before that. So the properties that we have to more focus on the material dryness, whether the material are dried or not properly, the material's particle size, means dp10, dp50, dp90 for both anode and cathode, the mixing speed of my mixer, say planetary mixer, how much time we have to mix the slurry, The homogeneity we have to check whether the particles or whether the materials are mixed together or not. Is there any phase separation available or not? So if there is a phase separation, then the slurry is not good for coating. Then slurry particle size also we have to check through scraper. Then slurry viscosity with the time interval. So here we have to understand the rheology or do a rheology study. So it's a kind of fluid behavior we have to study, whether it's a Newtonian fluid, whether it's a pseudoplastic or dilatant fluid, or how it is behaving. So again, there are some problems which are associated with all these issues. So if the material is not properly dried, the lumps will form inside the slurry, and that is not good for the mixing, and the mixing is not proper. Another is non-uniform mixing due to particle size variation. So if the particle size is non-uniform or it is very diverse, for example, dp10 is 5 micron and dp50 is 15 or 20 micron and dp90 is 30 to 35 micron, so it's a vast range, and the slurry mixing is not proper. Another thing is, if the slurry viscosity is too light or the slurry is too thin, then it is not easy to coat. So that's why we have to fix the slurry viscosity, and we have to continuously study this behavior as well, how my slurry viscosity is changing over the period of time. Then another thing is gel formation. This is more common issue in the cathode slurry, where PVDF is, it is not tolerating the water. So if any water or any moisture come into contact with PVDF or let's say NMP, then my gel formation will happen inside the slurry. So this is like the cathode slurry we have to make inside the dry room, or let's say less than 1% RH when we are starting the cathode slurry mixing. So this is the norms that we have to follow during the NMP or PVDF mixing scenario. Another one is the phase separation. So I'm showing you some images here. You can see some white patches over the slurry. So this shows the phase separation because of the moisture in the NMP itself. And if PVDF has the moisture, then it has a lump. So this is an image of PVDF with some moisture, so it has lumps in it. So the material has to be properly dried, as well as it is under its shelf life. So we have to check all these properties before starting slurry mixing.